Hello, this is Mr. Craig, and this is day 6. And today's topics deal with percent composition, which will lead us into empirical formulas, which will also then lead us into molecular formulas. When we talk about percent composition, first question here says calculate the percent composition by mass of the following compounds. Percent composition is talking about how much or the percentage of the certain substance that exists in that compound. So when we do a percent composition by mass, the first thing that you need to do is, first of all, find out what the total mass of the compound is. So the best way to do that is to get your periodic table out and then go through and find the molar mass, which we did in the last topic or last discussion. So in magnesium sulfate, we have 1 magnesium, which has a molar mass of 24.3. So we can go ahead and write down 24. Whoops. Let's make sure we're in the right thing here. Okay. So 24.3 grams, and that's per mole. Plus we have 1 sulfur, which has a molar mass of 32.06 grams, and again, that's per mole. So we'll add that as well. And the oxygen, we want to add all the oxygens here. So in this case, we actually have 4 oxygens, and the molar mass for oxygen is 16 grams per mole. And again, make sure that you have your periodic table out as well so you can do this. And then once we have all these masses for each of these, then we can do a calculation to find out what the molar mass of this substance is. So get your handy-dandy calculator out. And yeah, I'm not a big fan of the Microsoft calculator, but it'll do what we want it to if you're careful. So 24.3 plus 32.06 plus, and I'm going to use print. Oh, I can't. I know that 4 times 16 is 64, so I'm going to go ahead and cheat on that. So 4 times 16 is 64. So my total mass for the magnesium sulfate is 100.36 grams per mole. So 120.36 grams per mole. Okay, and again, these are all per mole. Don't necessarily need to do that for the percent composition. All right, so now that we have the total molar mass of our magnesium sulfate, now let's find out what the percent for each element is. So percent of magnesium. Okay, the way we do that is we're going to take the total mass of magnesium, or the mass that the magnesium has in magnesium sulfate, and then we will divide it by the total mass of the compound. So again, if I want to find out what the percent by mass of magnesium is, well, I have to make sure I have all the mass that magnesium contributes divided by the total. Then I will multiply that by 100. Now you'll notice I didn't say by 100% because that's a different calculator operation there. And I'm not a big fan of this calculator, so I'm not even going to try. All right, so I have 120.36. There is no memory or answer button on this. Your calculator may have that. I would highly recommend that you know how to use the answer button because it'll save you time. It really will. And once we get back together as a group in school in August, say, hey, Mr. Craig, I never found that answer button. Could you help me out with this? Because it's going to save you a lot of time and effort. And if I had the ability to show you my calculators that I have, the Casio and the TI, I definitely would show you where that answer button is. All right, so I'm going to take 24.3 divided by my total mass, which is 120.36. And that gives me that value right there. So I want to multiply that by 100. So I have 20 point, what was that, 1? I think it was 21. 20 point, we'll say 2. Let's just go 1 decimal. So we'll round that up. So the mass percent for magnesium is 20.2%. All right, so let's find out for sulfur. Okay. So for sulfur, we have 32.06 grams. Now, you'll notice that you're probably saying, well, where'd you get this this 32.06? again, I'm just assuming that I have a 1 mole. I have 1 mole of the magnesium sulfate. So I want to find out that percent. Now you can find out for any number of moles. However, it's going to be a little more work, and it's much easier if you just make it for 1 mole of the substance. All right, so we have our, let's clear that out. So we have our mass of our sulfur, which is 32.06, and I'll divide that by the total mass, so 120.36, and then multiply that by 100. So 26.6%. Okay. And then if you know that the oxygen is the last element, then you can add these two together and subtract it from 100%, and you should get the same answer as what I'm about to show you, which, again, we said that the total mass of the oxygen, 4 times 16, is 64. So percent by mass of oxygen is 64 grams. Divided by 120.36. Times 100, sorry. So, clear that out. Actually, I'll just show you. 4 times 16. Hold on. Times 16 is 64. And then divide that by the 120.36. And then multiply that by 100. So we get 53.2. And if we do our rounding correctly, then this should add up to 100%. So 0.2, 0.6, 0.2, that's 1. And then 6 and 3 is 9, plus 1 is 10, so I have a 0. And then I have 4, 5, 10, 100%. So here are my percentages by mass for each of these. Okay? Now, try the next one on your own. Go ahead and pause the video here and attempt that if you haven't already attempted that. What I don't want you to do is just have this as a viewing session. I want you to actually try these problems out before you try the homework for sure. All right, you've had a chance to work this out. So again, we want to find out the total mass. So from your periodic table, we know that sodium has a molar mass of 22.99, if I can show it to you. 22.9, as it says here. I think on our periodic table, let me see, I've got some in my room here. I think it says on your periodic table 22.99. It does. So let's stick with the 22.99. I don't know why that says 90. I apologize for that. Oops. Okay, so 22.99. Get my pen back here. So 22.99 grams plus carbon, which has a molar mass of 12.01. Come on, mouse. 12.01. And we have 2 of those, so 2 times 12. Whoa, come on. 01 grams. Plus we have 3 hydrogens, and a hydrogen has a mass of 1.008. And oxygen, which we just did a second ago, has a molar mass of 16. Okay. So adding all that up, let's get the calculator. Boy, this mouse doesn't want to do anything. Move you over so I can actually do this. All right, so 22.99 plus 24.02. That's 12 times. I'm sorry, 2 times 12.01 plus 3.0. What would that be? 3.2? Oh, sorry, 2.4. I just erased it all. That was dumb. All right, so 22.99 plus, and I hate this calculator, 24.02 plus 3.024 plus 32. Okay. So hopefully the molar mass is 82.034. And that's grams per mole. Now hang on a second. I'm going to run my calculator. calculator because I think it's going to bore you guys to death as you watch me type it in. I just want to double check and make sure that the Microsoft calculator is good. You know, guys, I don't trust this. Okay, 82.034. Good. All right, so to find the percent, we're going to do the same thing where we're going to do the... Come on. This thing is fidgety today. So percent of sodium is equal to 22.99 grams over the total mass, 82.034 times 100. I'm going to do it on my calculator. 22.99 divided by answer times 100. So 28% roughly. 28.0. Let's go one decimal place. Okay. And those are, should say percentages. And then the carbon, we have 24.02 grams over the total mass, which is 82.034 times 100. My pen is not behaving today. 24.02 divided by 100. So 29.3%. Okay. And then the hydrogen is 3.024 grams over 82. That should be a small number. Times 100. And you're probably asking or telling yourself, man, he's showing a lot of work. Guys, for the AP exam, they're going to expect everything that I am doing right now. So what the AP exam does not want you to do is just write down the answers from your calculator. They want to see what you're doing. So 3.7% roughly. And hopefully your pen will work. And then we have oxygen, which is 32 grams. Times 100. So 32 divided by 82.034. So around 39%. Okay. Here's a real quick check. Type all these values in. So about 39%. And again, these are rounded, so you may be off by a decimal value or two. Plus 3.7, plus 29.3, plus, what is that, 28.0? 100 exactly. So there's your percentages. Okay, and that is a 3 up there. All right. Let's look at the second question. Calculate the empirical formula for a compound containing 71.47% calcium and 28.53% oxygen. Empirical formula. Let's review what empirical formula represents. From General Chem, and I think we did this in the first half of the class, maybe. No, that might have been second half of the class when we talked about moles. Yeah, it was the second half of the class. Empirical formulas, again, is the chemical formula that has the smallest whole number ratio of values. So empirical formulas, when you look at ionic compounds, every ionic compound is an empirical formula because we always want to have the smallest whole number ratio of values. However, with molecular compounds, you could have things like we could have a CH2O, and then we could make a molecular compound, which is what it is, where we could have, say, a C18H, come on, 36 and O18. Now, that is a compound that exists. However, this is the molecular formula where this is the empirical formula for this. Okay, so again, for this compound, we can reduce these down to this. So this is the empirical formula. The empirical formula is important, especially with organic type compounds, so that we can find out what the percent composition is. And then once you determine what the molecular formula mass is, then it's very easy to find out what that formula is. So it's a nice little strategy. It's definitely a skill that you need to know when working out AP type questions. So empirical formulas, everybody should know how to do these. All right, now my suggestion is if you're ever given percentages, and you don't have to do it this way, you can do it the long way if you want, but if you're ever given percentages, pretend that you are given a 100-gram sample of this compound. Whatever this compound is, we don't know what it is, but we'll say that we measured out a 100-gram sample. Knowing that you have a 100-gram sample, what is my mass of the calcium? If I know that I have 71.47%. If you have a 100-gram sample, that makes this very easy. It changes that percentage into a gram. So you have 71.47 grams of calcium, which also means that we have 28.53 grams of oxygen. I'm telling you, there's many ways that you can do this problem. This is the easiest way. If you're given the percentages, work with the masses. Pretend that you have a 100-gram sample. Now, if you're given gram amounts, okay, don't try to figure out the percentages. That's not necessary. Because what we're going to do with empirical formulas is we're going to do a mole ratio. So if you want to find out what the smallest whole number ratio of the elements are, we have to do a mole ratio. Because if I have 1 gram of calcium and compare that to 1 gram of oxygen, I do not have the same number of atoms. I do not. Why do I not have the same number of atoms? Because they don't weigh the same. In other words, oxygen has a molar mass of 16 grams, where calcium has a molar mass of 40 grams. So if I say that I have 1 mole of calcium and 1 mole of oxygen, I then have the same number of atoms. However, we don't know if we have the same number of atoms. That's why we're doing a ratio. So even though the ratio may, or the percent might be skewed a bit, say that I've got, approximately 2.5, 3 times as much oxygen as I do calcium, that's by mass. That doesn't tell us how many atoms we have. So what we need to do is change these gram amounts or these mass amounts into moles. And that's what we did yesterday in yesterday's lecture. All right, so again, if you're given percentages, what my advice is, pretend that you're working with a 100-gram sample and change that percent into a mass. So knowing that, we have 71.7 grams of calcium. We want to find out how many moles that is. So in 1 mole of calcium, just looked at it a second ago, I believe it's 40.08. There's calcium right there. So 40.08 grams. And we'll find out how many moles that is, but not yet. Let's find out how many. We're going to change our oxygen. What's that, 53 grams of oxygen. Let's find out how many moles of that we have. And that's 16 grams. Now, since oxygen is not standing alone, if it's all by itself, then yes, oxygen is O2. However, it's not O2 if it's hooked up with calcium or some other compound. That's what we're figuring out right here. Okay? So we want to find out what those percentages or those ratios are. All right, so once we have our mass amounts and we have our molar masses, let's do some calculating. So 71.47, and again, I'm doing this on my calculator because it's quicker, gives me a mole amount of 1.783. And we don't want to round too much here, so I'm going to go out 4 decimal places just to be safe. Okay, I'm going to erase that too. And we don't need that. Okay. And then 28.53 divided by 16 gives me 1.7783. We'll say 1. All right. Now, when we have our mole amounts, then we wish to compare the mole amounts to each other. So when doing empirical formulas, ask yourself, from all these mole amounts, which one has the smallest number of moles? Well, I hate to tell you guys, but these are so close together, they are the same amount. So whichever one has the smaller amount, that's the one that we're going to divide by. Okay. So you will always, mercy, this pen is not behaving today for some reason. So that is a 1, and this is like a 0.999 something, 99, which is very, very close to 1. So it is safe to say that we have a 1 to 1 ratio, which means that my empirical formula is CaO. Now, hopefully, when you read the question, you go, oh yeah, calcium's got a +2 charge. Oxygen's got a -2 charge. It should be a 1-to-1 ratio. That's a check. Don't say that I'm being mean to you by giving you a problem like this. This is an easy way to check yourself to make sure that you're doing the work correctly. Okay? Now, there are some degrees by which we need to do some rounding, and I'll talk about that. Hopefully I've got a problem that'll cause us to do that here in a moment. Oh, looks like number 3 is a good one. So, again, what we want to do, if you're given percentages, pretend that you have a 100-gram sample. If you have a 50-gram sample, you just have to change and find out how many moles. The key is with empirical formulas, we need to get our mass amounts or our percentage amounts to moles. We have to work with moles. That's the only thing that's equal on the periodic table. And how do we know that? Well, when we look at our values or our masses on our periodic table, that tells us how much of that we need to have 1 mole. So if I have 12 grams of carbon and I have 52 grams of chromium, I have a 1-to-1 ratio. In other words, I have 1 mole of each of those based on those amounts. Now, we still have to find out moles. Let's just leave it at that. All right. Look at the next question. Number 3 says calculate the empirical formula for a sample that contains 251.85 grams of carbon, 14.09 grams of hydrogen, and 149.12 grams of oxygen, in that order. Now, normally I won't have in the question that. However, whatever the order is that the elements are given to you in the question, that's the order that you want to write these compounds out in. So keep them in that same order. Now, you'll also notice that you don't have percentages, but you do have masses. So we're good to go. We're ready to plug in these mass amounts and calculate how many moles we have. So let's start off with our carbon. So we had 251. Let me pop this up. So we had 251.85 grams of carbon. And from the periodic table, 1 mole of carbon weighs 12.01 grams. So we'll get a number there. And then we have 14.09 grams of hydrogen. And from the periodic table, hydrogen weighs 1.008 grams. We'll calculate that here in a moment. And then we have 149.12 grams of oxygen. And from the periodic table, that's 16 grams per mole. All right, so let's get some mass amounts here. So get your calculator out. 251.85 divided by 12.01. And again, don't round too much. I have 20 point, we'll say 97, and we'll go 4 decimal places, 00. And that is moles. Okay, moles. Those are moles. Those are really important to know that those are moles. All right, 14.09, I'm doing hydrogen, divided by 1.008, which is 13.9781, and again, moles. And then the oxygen, 149.12 divided by 16. wow, that's a nice number, 9.32. That's all the calculator says, so we don't have to round it. Or, whoops, 32. Yeah, that looks sloppy. So 32 moles. Okay. From this, which one has the smallest number of moles? Oxygen. So we're going to divide everybody by 9.32. Okay. I can do this one in my head. That's a 1. 9.32. 9.32. Because again, what we're trying to achieve here is obtaining a mole ratio. All right, so I'll do the carbon. So 20.97 divided by my answer, which is 9.32. I still have that in my calculator. 2.25. Okay, and we want to write that down. 2.25. That's my ratio. That's not. There's no unit on that because even though I didn't do it, I'm a bad example. I apologize. The moles cancel out. Boom, boom. Okay, so we're left with these numbers here have no unit because they're a ratio. Ratios don't have units. 13.9787 divided by 9.32 is 1. Says 49986. We'll make that 1.5. All right. Now, can we say, okay, well, since I have my ratios here, I have carbon at 2.25. Can I go carbon 2.25, hydrogen 1.50, and oxygen is a 1? No, you don't ever want to do that. Okay? Don't ever do that. We have to have whole number ratios here. So that's just bad. I apologize for even showing you that. I'm a bad example when I do stuff like that. So what we want to do is we want to erase that. We don't want to have that garbage there. All right, so what we need to do is obtain whole numbers. Probably the best and easiest way to do that is, let's see, I've got empty space up here since I erased the last question, is that sometimes we're going to get decimal values. And I promise you, the questions that I make will follow these rules. And I have noticed this in the last 15 years on the AP exam, that they do the same thing. So you're going to find out that what Mr. Craig does in class is what the AP exam does. So you're going to be going, wow, some of these questions sound like Mr. Craig's. Well, you're going to find out that I'm a thief. I steal a lot of questions from past AP exams. And the format, I change the names and the numbers, but I'm trying to keep the same format there. All right, so here's what I want you to do. If you get a decimal value, or I'm sorry, whoa, what happened here? Okay, we get, say, a ratio where it ends in 0.0. Hey, life is great. We don't have to do a thing. We're good to go. We don't have to do what we're going to do here in a second. However, if you get, say, a 0.25, don't round down. We never round down on the ratios. Okay, and I'll give you an explanation here in a second. If you get a decimal that's 0.33, or decimal that's 0.5, decimal that's 0.67, decimal that's 0.75, okay, or back to that 0. Okay, if you get a decimal value, probably the best thing that you want to do is if you get one of these decimal values, is you want to change it to a fraction. Now, I will get you very, very close to these values, okay, or even that one. Okay, what I will never do is like give you a value where it's like you get a decimal 0.71. So it's like halfway between here and here. It's like, well, which way do I go, or which way is it? If you get a decimal value on your ratio, okay, that's this over here. If you get a decimal value on your ratio that's 0.71 or something like that, that it's between two things evenly, you messed up. I'm going to be honest with you. You messed up. Now, on your mole amounts, the sky's the limit. We could have anything on our mole amounts, but our ratios, we won't be that far off. All right, so if you have, again, if you have some weird number like 0.71, or another good one is, somebody told me, well, I got 0.29. Well, that's right in between here. That doesn't work. That's a bad value. So you have to check your math again. But I will get you very, very close. I'll get you within .01 or .02 of one of these 5 here, or even that 0 there. Okay, so we want to change these to fractions. So 0.25 is a quarter, 0.33 is 1/3, 0.5 is 1/2, 0.67 is 2/3, and 0.75 is 3/4. So we work from very, very easy fractions. Now here's the thing. We want to, knowing that we have this, we want to change these values here to not read as 2.25, but, erase please, okay, change it to read as 2 1/4. Oops. Okay, 2 1/4. And then we want to change this 1.5, okay, not to read as 1.5, but now as 1 1/2. Okay. So again, whatever your decimal values are, which is great, and this is ratios only, ratios. Okay, not moles. Mole amounts, we don't care. We could have anything we want for these values. So it doesn't apply to moles. It only applies to ratios. So once you have your ratios and you come very close to one of these 6, okay, change it to a fraction. Obviously, if you're at 0.0, you're good to go. You don't have to do anything. The reason why we need to change it to a fraction, because it makes our life so much easier. So now that we have 2 1/4 and 1 1/2 and essentially 1.0, now we can get whole numbers. How do we do that? Well, whatever your value is here, that's what we're going to multiply everybody by. So in this case here, we're going to multiply this by 4. That gets rid of my fraction. Okay? If you multiply one thing by that, you have to multiply everybody by that. Got it? Multiply one of them, you multiply everybody. Okay? So that gets rid of this fraction. However, if I multiply this, I'm now going to have, what is that? 1 1/2. Oh, bro, I can't do that in my head. Gives me, does give me a whole number. Okay, so that'll actually eliminate it. And the reason why is because the 2 here, if I multiply this by 2, it'll change that to 3, but then I have to have that 4 there. So once I multiply everybody, check and see if you have whole numbers. Okay, well, this one's a whole number. This one we just did was a whole number. And this changes that to 9, I believe. Double check. 2 1/4 times 4, I believe, is 9. Yeah. All right, so here we have whole numbers now. So the 9, the 6, and the 4 are our whole numbers. So our formula is C9H6O4. And that is our empirical formula. We cannot reduce that down any further. Now, if you wanted to, and again, hypothetically, we say that this is a 3 down here. Hypothetically, we would then need to go and multiply everybody by 3, because just multiplying this by 4 would not get rid of that fraction. Okay? All right. All right. Molecular formula. All right. When we work out molecular formula problems, the really nice thing is sometimes you'll be given the empirical formula and other times you won't. So if you're finding the molecular formula, you first must know the empirical formula. If it's not given, and in this question it is, because I'm a nice guy, if it's not given, then you need to do all of this work first before you can do the molecular formula. Okay? Again, remember from earlier on, and I think if you need to replay the video because I think I erased it all, the empirical formula is the smallest whole number ratio for that compound, and then the molecular formula is what it is. Okay, so it has a much greater ratio than the smallest whole number ratio. All right, so let's work this one out. And good, we do have another one. Number 4, I believe it is. Determine the molecular formula for a sample of SNH, that's my empirical formula, with a molecular mass of 188.35 grams per mole. Okay, now when we talk about molecular formulas, there's a multiplier that we need to worry about. and the general equation, and it's not on our equation sheet, is that we're looking at the molecular formula mass, which is always given. Okay, so this is always given in our problems, over the empirical formula mass, and this you get to calculate. Okay, so the molecular formula mass over the empirical formula mass, and this is my multiplier. So we're given, or you are given, the empirical formula, which is SNH. Okay, so now what you get to do is find out what the multiplier is. And don't be sad, and don't be brokenhearted if the N happens to be 1. Okay, and I've seen that a lot on the AP exam, where you go through and find the empirical formula, spend a lot of time and a lot of effort, and then the molecular formula they give you is the same as the empirical formula, molar mass that you just calculated. It's frustrating. A lot of people freak out and they go, it can't be this easy, it can't be this easy. Well, it's only easy because you knew how to do the empirical formula problem. It's very, very difficult for those who don't know how to do it. So sometimes when you say it can't be this easy, you know what you're doing, and that's fine. Okay, I don't have any problem with you being concerned or worried that a certain problem is too easy. Okay, all right, so let's get right to this. Well, you're given the you're given the molecular formula mass, which is 188.35. Okay, we are not given the empirical formula mass, so we need to find out what that is. I think I may have some room up here. So sulfur, which has a molar mass of 32.06. Okay, so 32.06 grams. And then there's one nitrogen, which is 14.01. Come on, find it. So 14.01. And hydrogen, which we've been working with quite a bit here, is 1.008. And I'm going to let my calculator do this work for me. So 32.06 plus 14.01 plus 1.008. So 47, my empirical formula mass is 47.078. Okay, so again, this was given, this I had to calculate. Okay, the 47.078 I had to calculate from my empirical formula. Okay, so now that I have these two values here, and again, these are grams per mole, what happens to the unit in my multiplier? That's right, it goes away. It's a multiplier. Multipliers don't have a value. So 188.35 divided by 47.078. And this gives me 4.0008, which is 4. So N is 4. So what that means is, I'm going to change that N to a 4. And I'm going to multiply everybody in here. So it's S4N4H4. There's my molecular formula. Now, let's pretend that, say we had a 3 here. Again, we're done with this problem. Let's pretend that we had a 3 here. What would my formula then be? Yeah, if that were a 3, then you'd have S4N12H4. Okay, so it's a multiplier. So it's just like when you're looking at a polyatomic ion, and say you have 3 of those, and we're calculating masses, we want to use that as a multiplier. All right, so again, this is not the answer. This is the answer. All right, number 5. Try this last one on your own before you watch this part of the video, and I'm going to work it out because this summarizes everything together. And I think I may have enough room here. Let me see if I can scoot this up. So go ahead and pause the video for a second and work on this. Scoot this up. I think that's the last question. It is good. Okay. All right. Hopefully you've had a chance to work this out. So let's get right to it. And I'm going to try to go as quickly as possible because I know this video is getting pretty long. All right, so again, we have our sample of the stuff in order here. So nitrogen, phosphorus, and chlorine. And again, don't worry about it. It's not one of our polyatomics. So we are not given the empirical formula, so we must determine that. So 1 mole of nitrogen, 14.01, 26.73, oh, come on, and that's phosphorus, and that's 30.97. You'll get to memorize these as well. And chlorine, 61.18 grams. And that's 35.45 grams. And that's from the periodic table. And that's all the masses. All right, so let's find out how many moles of each we have. 0.09 divided by 14.01. So again, I don't want to round too much here. 0.86296. That might be a little overkill, but that's okay. 26.73 divided by 30.97. 886. 30, say 9. Okay, and then 61.18 divided by 35.45. It's 1.72. 581. All right, so there's my mole amounts. That is not my mole ratio. Notice I still have units here. So my mole ratio, I want to find out which of these is the smallest value. And these are relatively close. I mean, 2930. So we'll say that this one's the smallest. So 0.86296. Do that in my head. 0.86296. Even though that's 0.999 something, again, remember what I said about up here. Okay? It's going to be very, very close to 0 or to 1, whatever. So even though it's very, very close to 1, it's nowhere near the 0.25 or the 0.75. Okay, so it's nowhere near these two values, so we're going to round it. Okay, let's move on down. So it's very safe to say that that's 1. Now, if it were like if it were 1.05, you may want to check your calculations. You'll be within 0.02 to 0.03. You'll be very, very close there. Okay. And then down here, 86296. So 1 point, do I have that in my calculator? Divided by 0.86296. So 1.998. Boy, this is an easy problem for you guys. I feel bad for you. So my empirical formula is NPCl2. That's my empirical formula. Okay, so we did the first part. So we calculated the empirical formula, so we need to find out what the molecular formula is. Even though it didn't tell us to find the empirical formula in this question, it says determine the molecular formula. There's no way we can find the molecular formula until we find the empirical formula. Okay, so we have our NPCl2. NPCl2. And we need to find out what our multiplier is. Okay, so the molar mass, molecular mass is always given. Here it is, 347.64. 347.64, and that's grams per mole. And we need to find out what this is. So let's find out what the empirical formula mass is. So the empirical formula mass is 14.01 grams plus 30.97. And again, I'm going molar masses here. Plus 2 times 35.45 grams. Now equals, Actually, I made that a little too long here. That'll equal. All right, so 14.01 plus 30.97 plus 2 times 35.5. 115.88. Okay, so my empirical formula mass is down here. I just calculated that. That was given. So 347.64 divided by answer is equal to 3. So my N is 3. Okay, so 3. So now this problem becomes very simple. So N3, P3, Cl6. There we go. Okay, and I think that's all the problems, guys. Hope this video has helped. If you have any questions, by all means, email me. Molecular formulas, empirical formulas. I hope that you had a pretty good foundation in general chem, and I know that a lot of students are frustrated when they go over empirical and molecular formulas in general chem. And if you need more practice with this, by all means, let me know. I've got a bunch of problems that I can give you and you can work on. Okay. So if you do have any questions or concerns, please don't hesitate and shoot me an email.